Dear students, welcome to the third video lectures on thermodynamics. In the previous video, that is in my second video, I mentioned that the various terms are going to be introduced for understanding the thermodynamics. These are all the various terms that we have to understand without any ambiguity to understand completely the thermodynamics. Because understanding the thermodynamics largely depends on understanding these fundamental terms in the thermodynamics. Because without these terms, we cannot study the thermodynamics. Terms are first one is this is the group of terms system, boundary, and surroundings. The second one is the property of the system. The third one is state of the system. The fourth process, path, and cycle. The last one is various equilibriums that exist in thermodynamic study. Okay, so we'll see the various groups in detail. The first one is system, boundary, and surrounding. Most of the engineers thinking that the definition of the system is very trivial. It's not trivial. It is not at all trivial. We have to clearly identify the system because the identification of the system may differ from one engineer to another engineer. In the same equipment, if the two engineers defining the system in different ways, they will get the answers differently. So the identification of the system is very essential in studying the thermodynamics. If you are not understanding properly what the system is, then your calculation going to be giving wrong results. That is going to be error in it. Okay, so the understanding of the system is very essential. Okay, by definition, what is system? System is nothing but a definite quantity of matter. Here, just I mentioned in black box. That is, this is a definite quantity of matter in it. Okay, so whatever the matter in it is called as a system. Whatever the matter in within this is a, we call it as a system. The second one is the boundary. What is exactly the boundary is? Boundary is nothing but that outermost surface of the system. So it is a three-dimensional object. So the outermost surface, we call it as a boundary of the system. The understanding of the boundary is also very essential. And the last one is surroundings. Surroundings in most of the books that they are mentioning, the other than system, everything is surroundings. To me, it's not like that. The surrounding is the volume up to which the presence of the system is felt. Okay, so the presence of the system is affecting the surroundings to some extent. That is what we call it as the surroundings. So this is what my surroundings. Other than that, other than that surroundings, that portion may not be getting affected due to the presence of the system. Okay, what is the importance of the boundary? Yes, boundary is very important in understanding that interaction because we are more worrying about the interaction between the system and the surroundings in thermodynamics. In thermodynamics, system and surrounding interaction is very, very important. System and surrounding can be interacted in two different ways. So one is mass interaction. Second one is energy interaction. Oh, okay. Of course, along with that energy interaction, there is going to be entropy interaction also that we will see later. Okay. So, in time being, please understand the mass and energy interaction between the system and surroundings. Okay. Now, when you call a system and surroundings are interacted through mass, yes, very good. Then, whenever a mass entity or some portion of the mass, suppose some portion of the mass is crossing the boundary, whenever it is crossing the boundary, then only we can call the mass is being interacted between a system and surrounding. Either it can be transferred from the surrounding to the system or it can be transferred from the system to the surrounding, doesn't matter, but they are interacting in terms of mass. Similarly, energy. Energy is also going to be set as an interaction whenever the energy crosses the boundary. Certain quantity of energy, say if they crossing the boundary, certain quantity of energy E is crossing the boundary, okay, then only we can say yes, the system and surroundings are interacting. Suppose some energy is moving from one place of the system to the other place of the system, then we cannot say this is an interaction, and we are not bothering about the calculation of that particular quantity of energy which is being transferred within that system. So the definition of the system, definition of the boundary, and definition of the surroundings are very, very, very essential for understanding the mass and energy interaction between the system and the surroundings, because this is what our ultimate aim. You may ask one question: what is that necessary to calculate the interaction of mass and energy between the system and surrounding? As I already told you in my first video itself, the fundamental of thermodynamics is to calculate the amount of energy that's going to be transformed from one form to another form, or it's being transferred from one place to another place. So the calculation of energy is very much essential. Along with the energy, the mass is interaction also very important, because mass can carry some energy in terms of heat or in terms of its pressure form. So the mass and energy interaction is very much essential for fulfilling the objective of the subject thermodynamics. And the entropy interaction is very much essential for understanding how efficiently these interactions are going to be. That is the purpose of entropy interaction calculation. But at present, please understand the definition of system, boundary, and surroundings. Those are all very, very essential for understanding other interactions. Without this, you cannot study thermodynamics. Somebody will think that system definition is very trivial and they just jump over it. No, please concentrate on the definition of the system, boundary, and surrounding. This is your first job in any thermodynamic analysis. So this is what system, boundary, and surroundings. The second one is property of the system. Yes, now we defined what a system is. What is my system? With a definite quantity of matter, and we have clearly mentioned the boundary. At present, I'm going to introduce some of the properties of the system, and later I will explain you each and everything in detail whenever we move on to the next videos. In the property list, I have grouped into two: one, that A group and B group. See, in A group, I am having pressure, specific volume or volume for that matter, temperature. In the P group, internal energy, enthalpy, entropy, fugacity, Cp, and Cv. All those things will be introduced in the future videos. See, what is the difference between this group A and B are? This A group, these are all, we call it as a basic properties. These are all very powerful properties because we can directly measure these things. We can directly measure the pressure, volume, temperature quickly. Okay, so and this B group properties are nothing but they are going to be calculated using the measured properties. Usually, some of the properties can be directly measured and some other properties can be calculated using the measured value. Just now you understand these are all the properties. Properties are nothing but the characteristic of the system. How, at what pressure that particular system is, at what is the volume of the system is, at what temperature the system is, like that. So it's like a characteristics of the system. That is what property. And further definition of the property will come in my next lectures. Now, coming to the third one, state of the system. Now, we defined what is different properties. Properties nothing but identifying the characteristic of the system. Now, what is the state of the system? Say, if I tell only one pressure, will I uniquely define the system? No. One system is at a, say, for example, 10 bar pressure. Another system is also at a 10 bar pressure. I cannot say both are same, because the 10 bar pressure, I can say it may be a 10 bar pressure of oxygen. Say, for example, both are oxygen. One is at a 10 bar, another is also at a 10 bar. I'll just draw the figure for you to understand clearly. So, okay, this is, say, 10 bar pressure. Similarly, I am having another 10 bar pressure. Can you say both A and B are same in all other aspects? All other properties are also going to be same? No, it's not possible to say, because though I know that same oxygen is here, I may have at a different temperature, T1, TA, this is at TB. So now I can say uniquely, yes, I can calculate all other properties using this pressure and temperature of the TA. Now I can say that unique. Suppose if both the pressures are same and TA and TB are also same, then I can say the state of the system is uniquely defined. So what is the state of the system? We are attaching certain number of properties to a system, then it is called as the state of the system. Here, the certain number. What is that certain number? It is the minimum number of properties required to identify the unique condition of the system. Very good example I can say is, suppose a person is living in a particular district of a state. If you want to identify unique identification of his address, if I say he is living in a particular district of a system, no need to tell the state, because already you defined the district. So district is within that particular state. That is, there is a link between the district and state. Similarly, some of the properties are interlinked. So you need not to say. Say for example, if I take for example a simple system of oxygen. Yes, yeah, chemically, what is that chemically homogeneous oxygen, if you take it, if I mention the temperature and pressure, is more than sufficient to define it uniquely, because other volume and other properties are interrelated. Once you specify the temperature and pressure of it, automatically volume and other properties are fixed. You cannot attach a volume to it when you define a temperature and pressure. So it is a minimum number of properties to identify the unique condition of the system. That is what we call it as a state of the system. Minimum number. That is very much essential. So next, immediately the question will come to you. What is the minimum number of properties that we require? Yes, I can easily say that it can be easily calculated using the Gibbs phase rule. Sorry, we can easily calculate using the Gibbs phase rule. That is, F plus P is equal to C plus 2. That is, the F is the degrees of freedom. That is nothing but minimum number of parameters or properties required to define a state of a system uniquely. So P is the number of phases involved in that system. C is the number of components. So for our example, oxygen is a single component system. It's a single phase system. So if you replace P as 1 and C as 1, then you will get F is equal to 2. That means I require two properties to define the state of that particular system. Here, my my system is nothing but oxygen of certain mass. This is my system. Okay, so now to define the state of that particular system, I require two properties, either pressure and temperature, or temperature and volume, anything for that matter. If you define the temperature and volume, you can calculate the pressure. Or if you define the temperature and pressure, you can calculate the volume. Or if you define pressure and volume, you can calculate the temperature. Once you know the PVT, then all other properties easily can be calculated. So that is what the state of the system. Once you know how to define the state of the system, next we have to understand what is the process, what is path, what is cycle. See, now we take that simple example of the previous definition, oxygen of certain quantity in a closed vessel. That is what I have taken. Say this is my oxygen. So, in the previous example, I told you that we require two properties to define uniquely the state of this particular system. So, whenever you are in a position to take the two variables or two properties, that thing can be marked in a two-dimensional graph, say x and y. This x and y are going to be two properties. If you know the x1 and y1, you can mark that as a state 1 of that system. This is what state 1. Similarly, I can mark 2, 3, 4 different states of the system. If there is a methodology you are adapting onto the system to change the state of the system from state 1 to state 2, in that way, that particular process is called as a that particular what is that methodology is called as a process 1 and 2, process 1 to 2. So for example, suppose you assume this is the oxygen is occupied between a cylinder and a fixture piston. Now I am having a property of pressure and some volume. Suppose if I am in a position to compress this piston or moving the piston towards down, then the piston will come here, new position. In that case, the pressure will increase and volume will come down. So this state 1 will move to state 2 this side. That is, volume will come down. This is a pressure volume diagram. Suppose if it is pressure and volume diagram, the volume will come down and pressure may go up. So what type of process, those are all we will discuss in our future lectures. Now you understand, this is what we call it as a process. A process is nothing but some activity that is going to change the state of the system from state 1 to another state. That is what we call it as a process or path. Suppose if you have more number of process, all the process put together, the final state is going to be the initial state. Say, for example, in this case, process 1 to 2, 2 to 3, 3 to 4, 4 to 1. If all these things put together makes the system start from the state 1 and ends at the state 1. In that case, we call this combination of four process as a cycle. So a cycle is nothing but the initial state and final state of the system is going to be same. That's what we call it as a cycle. So here states is one x1, y1, x2, y2, x3, y3, x4, y4. These are all we call it as a state of the system, but not limited to only four states of this system. See, there are infinite number of states are there in this cycle, between 1 to 2, 2 to 3, 3 to 4, 4 to 1. All the points which is lying on this particular curve is called as states. But those states cannot be measured accurately. That we call it as a quasi-static process. See, I will explain you that quasi-static process in my future lecture. At present, I don't want to confuse you. You understand, this is what process, this is what the cycle, process or path. And if more number of process put together makes a system to move from the state 1 to and also ends at 1, that particular process called as a cycle. This is what the definition of a process and cycle. Now, the last definition for this lecture is various equilibriums that's going to be studied in thermodynamics. Say we have three different types of equilibrium exist. One is thermal, mechanical, and chemical equilibriums. So, what is thermal equilibrium? If there are two systems, if the two systems are there, say, sorry, need not to be systems. One A system is there, and its surrounding is there. If this system and its surroundings are all at a same temperature. Say, for example, this is T1 and this is T2. That is, system and surrounding is at same temperature. Then you will not definitely expect any heat will flow from system to surrounding or surrounding to system. That way we can say the system is in thermal equilibrium with the with its surroundings. This is what it is. Next is mechanical equilibrium. Suppose the system may have a movable fixture piston. If both the side the pressures are same, then you will not experience the piston will move to and fro in the system. Then we can call this system is in mechanical equilibrium with its surroundings. That is, forces are equal in the surrounding and system. Last one, chemical. The species in the system and species in the surroundings are chemically homogeneous, and there is no reaction is taking place, even though you are allowing it to interact with each other. In that case, we can say the system and surrounding is in chemical equilibrium. If all the equilibrium exists, then we can call that as a thermodynamic equilibrium. If the system is in thermodynamic equilibrium with its surroundings, then there won't be any interaction may take place. See, if thermal equilibrium is not there, you can experience that heat interaction. If the mechanical equilibrium is not there, you may experience the work interaction. If the chemical equilibrium is not there, you may experience both heat interaction or work interaction. Ultimately, I am concentrating how much heat and work interaction that's going to be taking place between a system and surrounding all the time. Please keep that in your mind because that is the objective of the thermodynamics. And these are all the terms that I just want to introduce. But apart from that, I am going to explain you what is the heat and work in thermodynamics. Please understand, as I already told you, the thermodynamics is dealing with the energy transformation and the energy transfer from one place to another place. In that, we are going to deal only with the two forms of energy. It's not two forms of energy, actually, it's a definition of two ways only, because heat and work. Heat energy, that you know very well, whenever a energy is being interacted between two system because of its temperature difference TA and TAB. The TA and TB are not equal. In that case, we call that form of energy as a heat energy. So, what is that work form of energy? All other form of energy whose sole effect, whose sole effect can be reduced to raise the weight against the gravity, then that particular form of energy is called as work form of energy. Say, for example, if it is a mechanical form of energy, we can connect it to a pulley and that pulley can lift the weight. Or if it is a electrical form of energy that's coming out from the system, in that case also we can connect it to a electrical motor which can run the pulley to wind the rope to lift the weight against the gravity. So we have only two form of energy in thermodynamics, that is heat and work. So in thermodynamics we have only heat and work will be considered. No other forms of energy is going to be. Actually, it's not a form of energy that be convenient. We call all the energy whose sole effect can be reduced to raise the weight against the gravity as a work. So only heat and work will be considered in thermodynamics. So that is what just I want to give an introduction to some of the terms in this particular lecture. But please keep that in your mind. I have given only the introduction of the terms. The explanation of the terms will be coming in my subsequent videos. Please follow that, and definitely I will enlighten you what is the definition of all these things. What are the important points that you have to keep it in your mind for understanding the various terms in detail, so that you can understand thermodynamics very finely. Okay, before going to the elaboration of this properties or various terms, I want to introduce or explain you in my next video the zeroth law of thermodynamics in detail. Because though some of them thinking that this seems to be a trivial, so a lot of things are there in the zeroth law of thermodynamics development. I will explain you in my fourth video only the zeroth law of thermodynamics. In my fifth video onwards, I will explain all other terms what I explain now in my third video. Thank you very much for your listening. Thank you.